Hello, welcome to Convergence. My name's Michael Dorn. I'm a California attorney. Albert Einstein said that among the most difficult problems in all of physics is the Earth's magnetic field. I argue as a California attorney, and I've been doing it for 25 years on different bulletin boards in different places where people have discussed climate change. I argue that the Earth's magnetic field is amongst the most difficult problems in all of biology. Today I want to discuss the MSU data. So what is it? Well, University of Michigan Michigan State University has compiled data over time, and they're checking to see where the warming in fact is occurring according to the satellite data. And what they've discovered is basically that the further north you get into the northern hemisphere, the warmer it gets. Just looking at this here, looks like about 0.6 Celsius. At the South Pole though, there's no change. So the question is, why? About 20 years ago, I was on the New York Times bulletin board discussing climate change arguing with an operational meteorologist from Chicago who identified himself as Tom. As you know, that's how it goes on the internet. Sometimes you don't know who you're dealing with. And I'll tell you who I am. And Tom was a skeptic, but he was a little bit sadistic. He liked to make fun of me because at that time I was a warmer, but I was changing my views. I was becoming neither a warmer or a so-called skeptic. But what Tom liked to say is, well, how come if CO2 is a greenhouse gas, the southern hemisphere is not warming as rapidly as the northern hemisphere? You would think that what you would see would be the southern hemisphere taking on CO2 as a greenhouse gas. There's more water there, so the feedback of water could occur, and you would expect to see greater warming in the southern hemisphere. In fact, you don't. You see it in the northern hemisphere. I've seen many papers by warmers trying to figure this out and to justify and to rationalize what their theory is. For instance, even Hansen, who is retired, wrote a paper and blamed the temperature differences between the hemisphere on aerosols. So he felt like, he surmised, speculated, that because the northern hemisphere has more industrial activity, that the warming there was more acute. Well, I'm going to even add another part to it that maybe is not even in the calculus here. And that is, the sun and the earth do not have an equal distance over the year. In fact, the orbit around the sun is elliptical that the earth takes. And during the winter time, this shape of orbit brings the earth closest to the sun. And so you would think that not only during the winter time, when the earth is tilted and pointing at the sun, that you would see with this close elliptical orbit, it's part of the Milankovitch cycle, by the way, you would see a greenhouse gas effect being strongest in the southern hemisphere. But in fact, that's not what we see. If you've seen any of my prior episodes, what I suggest, what I believe to be true, is that CO2 is not interesting as a greenhouse gas. It might be a chaotic input, but it's a dampened system, And CO2's role is directly in clouds, not as an amplification. And it has to do with cloud microphysics, that when carbonation gets into clouds in the context of large-scale, low-frequency electromagnetic currents, the freeze rate is changed, and clouds organize with carbon dioxide. So this then, when you see the MSU data skewed, is consistent with this idea. Why? Well, because 90% of lightning occurs over land, and there's more land in the northern hemisphere. In fact, you can also see some patterns with respect to what is occurring when you look at some of the land features around the world, the large-scale ones, as antennas. There's also, if you're looking at an electrical complexity, a pattern or patterns that have to do now with where carbon dioxide is in the ocean, and then therefore where surface lows draw that carbon dioxide into clouds, and it causes them to have organized behaviors where that's occurring. And so, for instance, in the past, in a dampened living Earth system, lightning would produce and would fix nitrogen into soils, help soils grow better, crops and other things that would increase carbonation in an area, and then that carbonation flows down in a organized way down river systems and carbonates the nearshore oceans, where again this process of decarbonation with surface lows would bring that carbonation back into the clouds and provide feedbacks. So what we're seeing, for instance, with the drought here in the West is a impact of different types of electrical things that affect carbonation in the nearshore oceans. One of them is Hoover Dam and other dams up and down the West Coast, which reduce sedimentation and the amount of methane hydrates that are allowed to exist along the ocean. And then when you contrast that with fertilization and the dead zone in the Gulf of Mexico, you get more patterns that are related to electrical conditions. Finally, if you look at places like the Iron Range, where iron has been removed, and the electrical implication of that, or you look at Alaska as an antenna in the Aleutians, you look at South America and Antarctica with the basically antenna-shaped features there. And then simply, if you consider that the tropics are warming a little bit, decarbonation events are moving towards the poles. So basically, it's about where storms are moving. And there's a number of cooler anomalies in the Pacific Ocean, according to the MSU data. These are all indicative of a different mechanism than CO2 as a greenhouse gas. So there's also seasonal implications too. So for instance, lightning comes in a double peak, and the northern hemisphere gets more lightning because there's more land there and there's more lightning. But also during the tropical storm season, the place where tropical clouds are don't immediately move back to the southern hemisphere. It's an intertropical convergence zone, it's called. And just in terms of where land is with Asia and Africa and South America, there's a little bit of odd shape things going on, that as you get to the winter time in the northern hemisphere, the summertime in the southern hemisphere, you have a specific change in the amount of lightning that has to do with the shape of the continents. So Africa has kind of a big wide head, and then it comes down to a narrow part, and as the intertropical convergence zone drops down, it drops to a more narrow part of Africa, so therefore the global input of lightning that Africa has changes throughout the season. And consistent with that, there are no tropical storms. It's a low point in tropical storms in December, as you're moving down into the southern hemisphere, and the southern hemisphere hasn't warmed. Another strange thing occurs, and the same thing is with South America, although it's not as a severe a change as with Africa. And finally, the Southern Ocean, the Indian Ocean is very unique that way too, because as you get towards the winter time and the intertropical convergence zone, it drops south of India, and when that happens, there's no more land. The monsoons go away, and the lightning from that goes away as well. So during the winter time, especially in December, there's very little comparative amount of lightning, and the Southern Ocean and the South Indian Ocean, the South Pacific, the South Atlantic, they haven't warmed up enough to be conductive for capacitive couplings to give you a tropical storm. When you get past December into January, February, March, at that time, even though you might see a movement north, those oceans have warmed up enough to have capacitive couplings and to hold charges and to get tropical storms. So higher carbonation in general is going to be a signal noise problem for the dampening that a living Earth does electrically. And it's going to be expressed, this signal noise problem is going to be expressed differently throughout the year, and it's going to be expressed differently in terms of anomalies that you're seeing from the MSU data. Again, it's skewed. It's skewed towards the northern hemisphere. It's kind of like taking a 100 and a 200 watt light bulb, and let's say it's now 200 watts in terms of the behavior, not the greenhouse gas behavior, but more or less the way clouds organize and trap heat and the way they move is going to be more expressive in the northern hemisphere, but you won't know this until you flip the switch. And that's indeed what we're seeing, is that when the lightning occurs in the northern hemisphere, yes, it's showing these warming anomalies. In a prior show, I talked about a paper that talked about how the troposphere is warming slower than expected, and the stratosphere, where there's a lot of electrical particles, is cooling faster than expected. So that's kind of a top-down analysis of what's going down. This is a north-south analysis, and it points to clearly points to an electrical complexity. The greenhouse gas theory really isn't capturing what's going on with dams and how they're changing when carbonation occurs, and then therefore how feedbacks occur. They're not immediate enough. They're not subject to having the sand and other mud and detritus and things like that flow down rivers that provide an environment for methane hydrates and a sensitivity to rivers. And we're really starting to see that in California, where the drought now, I wouldn't even call it a drought. It's kind of like the Ural Sea, where it just dried out. and there definitely were dams involved in the Rail Sea. So what's going on here needs to be looked at as an electrical complexity. And what happened when I was debating climate with this operational meteorologist, Tom, when I started to say, well, that's not a sign of a lack of CO2 here, it's a sign that there's an electrical complexity, and what I've been talking about all along in clouds is what's occurring. It's not a feedback to warmer air from carbon dioxide as a greenhouse gas, but rather it's directly in clouds in the context of electrical fields. There's more currents, there's more, the global electrical circuit is more active during the summertime when there's more lightning in the northern hemisphere. There's a double peak. At first in the spring, you're going to get a lot of lightning from frontal activity. And then in the fall, when the oceans in the northern hemisphere have warmed up and you start to get spring lightning in South America and Southern Africa, that's when your tropical storm season is the most active, and that's the biggest time of lightning globally. And it's why tropical storms have not become as active in any basin except the Atlantic. It just has to do with lightning. It has to do with when the Atlantic is still warm and when there's a peak of lightning. And so higher carbonation is resulting in some inputs, and there may even be some aspects of the greenhouse gas that are in play, but it's a dampened system, and CO2 is just as a raw chemical is meaningless unless you're talking about the signal that life can provide against that. So we have to start looking at carbon dioxide as an electrical element inside clouds before we're going to be able to understand what's going on and bring about policy that actually matters and helps the situation. Because it's about cloud behaviors. When you have 4 watts per meter squared, what CO2 as a greenhouse gas does. This is all textbook stuff that I'm talking about. And you're talking about the difference between pre-industrial and industrial period of time. And so you're talking about 1 or 2 watts per meter squared. And then you're talking about clouds, which are 100 watts or 200 watts per meter squared if you're talking about cirrus clouds. And fog is minus 100 watts per meter squared. Energy just gets reflected back out into space. So they're not, these numbers are not even on the same power. You're not talking about even in the ballpark of energy. It's about cloud behaviors. And if you think about it, we're here. Life is here. We exist. It's been over millions of years, a living Earth has kept temperatures in the Earth's magnetic field to within a living range. If the Earth's magnetic field didn't exist, we'd be Mars. If it's too strong, we're going to capture too much greenhouse gas. So Earth's life had to dampen this, and that means that if there was some reason that ambient carbon dioxide levels went up, then the feedback had to be stronger than the random thing that was occurring. So it has to be electrical. It has to be. Otherwise, we wouldn't be here. One argument I frequently have heard in these bulletin boards is that during the Carboniferous, and I've talked about this in a previous video, that when the Carboniferous was around, CO2 levels were multiple times more than they are now. So why is it any big deal? Why can't we just go back to the Carboniferous? Life was fine with a trace gas. In fact, plants grew better. But the problem is that during the Carboniferous, a lot of the land was over the South Pole. And so because most lightning occurs in the tropics, and because most lightning occurs over land, when most of your land was in the Southern Ocean, part of Pangaea, then you're not going to have as much lightning. And if you don't have as much lightning, then you're going to need to have a greater amount of a feedback to make the circuitry work and to make the feedbacks work. Otherwise, again, the Earth's magnetic field would get too weak, the atmosphere gets stripped away. In order to make that atmosphere, it's contextual to the proper atmosphere to modulate or dampen the Earth's magnetic field. It's contextual to where the land is. And it's the same thing now, what we're seeing with the hemispheric differences. It's contextual to to where the land is and where the lightning is and how much lightning there is in the global electric circuit, because that's what life is dampening. So in order for us to make effective policy and to talk about what things can be done to deal with climate change, even to understand how tropical storms work and when they occur, or other concerns, like if we're creating conditions for a neoglacial, and that is, you can talk about that in terms of as the tropics warm up, then the tropics hold less carbonation, and so storms have to move towards the poles. The other interesting thing that happens between the seasons is, as you get into the southern hemisphere's summer, or when the Earth is pointing towards the sun from the perspective of the southern hemisphere, the Southern Ocean is very unique in that it can be kind of like a common. And what you see on some of the lightning sites, like the Washington University Worldwide Network, the lightning monitoring there out of the UW, what you see is patterns of lightning occurring over the land, like South America, like Africa, and like Australia. But where those land masses are like in places where there's a gap between, there's a huge gap in the Pacific Ocean between South America and Australia. Well, why is that a big deal? If you have a common on the bottom, you start seeing these static field organizations where there's lightning over the middle between Australia and South America. And that's precisely why El Nino isn't interesting until that time. Is because only in the wintertime do you see these lightning, which again alters the cloud microphysics. You see the lightning set up in the middle, and warm oceans are more conductive than colder oceans, but colder oceans can hold more carbonation. So you have this dual thing going on, and the state of the science is more about coupling the behaviors of the ocean and the skies, but don't look at the fact that there is this electrical complexity that affects not just there where the oceans are warmer in the tropical Pacific where El Nino is, but it's known as a teleconnection precisely because, and it's a perfect word for it, because it's an electrical phenomenon. From where the lightning is in the central Pacific and where storms are and start, there are conductive pathways that then determine whether you're going to get rain or not, depending upon the ocean temperatures and then therefore the carbonation. But even looking at that, it's still a dampened system. It has to do with what flows down the rivers, where the carbonation is, and so forth, which is why dams are a big problem, is because they change the timing of when carbonation occurs relative to these different teleconnections. So again, that's my review on the MSU data, why it's skewed, why skeptics jump all over that, and why skeptics so-called skeptics, are not correct about not being concerned about carbon dioxide. It is what life, it's fundamental to life, and it's part of a feedback, the first feedback that we had on this planet to modulate or dampen the Earth's magnetic field. All right, good luck, and please like if you like, and please subscribe if you like as well. I appreciate it. Thank you.